Hello, this lesson continues from the previous lesson that we just started with example number 3 in the previous lesson. And there were some technical problems, and all the rest of the recording was not recorded. So I'm doing this again. So this might be a little faster than the recording that didn't get recorded. So feel free to pause and replay. Okay. Determine the domain and then solve for x. So this is the example that where we left off, right? So we first determine the domain. So we take the whole thing and we set it larger than 0. And this is solving a inequality, which is actually a quadratic inequality. So we take square root on both sides and we found a domain, which is such. And the domain can be expressed using the number line, right? And you can also see that we actually, if we are curious about the graph of the function, right? We're curious about the graph of the function. We can actually graph ln x squared plus x squared minus 1. Okay, ln x squared minus 1, if we graphed it, excuse me. If we graph this curve, we actually see it, this need to be adjusted, okay? So this software, right, it's actually like this. Make it to 3, 2, 5. Okay, so this will be the picture. I want you guys to see this picture because you're going to see some very interesting phenomena, right? We have two pieces, right? And this function actually is no longer one-to-one. It's no longer one-to-one. And this domain, the pictures show up in the domain. This picture show up in the domain. So if I put the domain in the picture, you're going to clearly see, okay, you're going to clearly see how the picture fall in the domain. Okay, so domain, right? So that red piece and another red piece. And the two circle. Those two circles are going to be shown so clearly on the picture. Okay, that's one, and there's another one. Okay, 1, 0. So if you see the domain and you see the picture, right? That's the picture of a logarithm, right? That's a picture of a logarithm x minus x squared minus 1. X squared minus 1. So this is the picture. Okay, and the red, these red horizontal line, these two pieces are the domain, and you can see the graph only show the domain, and there are two vertical asymptotes. Okay, the two vertical asymptotes, I'm going to graph them again, is right here. Oops. Okay, so that's one vertical asymptote, which we're going to draw a broken line. And the next one is this other one. So if you have this curiosity to graph this picture and you have the convenience of having access to graph it, you can graph it by hand. It's just a lot of work, right? But if you have a device, and then if that output equals to 2, right? There are 2 points of crossing. Okay, so that was the picture I showed earlier. There are 2 points that crosses. Okay, there are 2 points of crossing. Of course, we are to identify these 2 points. we are to identify these 2 points, right? So we're gonna graph the horizontal line is y equals to 2, which is stated by the equation if the output equals to 2, right? If the output equals to 2. If the output equals to 2, we draw the horizontal line, and then the horizontal line is as such, right? So I'm going to draw this y equals to 2 in the picture. And let's see. So what we want that to be done properly so you can see well, right? So we have 2 solutions. We have 2 solutions, right? And these 2 solutions are what we are going to find. Okay, so these 2 dots are what we want to find. And this picture should be put at the end of it because we find it later. So now we're going to identify the points. Obviously, the point you see is not 3. The x value is not 3. It's less than 3. So it's very difficult to guess. It's very difficult to guess, right? Now, so here's how we solve the equation. So here's how we solve the equation. So we still do it algebraically. By definition, we got that, right? And then x squared minus 1 equals e squared, and x squared equals 1 plus e squared, and take square root, and the absolute value equals to square root of 1 plus e squared. So for that, we have 2 solutions. And this, of course, is the model for solving solving absolute value equation. So we found the 2 solutions. Eventually, we did, right? One is here. When input is this, the output is 2. When input is that, the output is 2. So these are the 2 points. These are the 2 points. So the algebraic steps we did help us to find the solution precisely. So these are the 2 solutions. Okay. Now look back as how we shall, look at the way we do it. Some people, when they see negative numbers, they automatically assume the negative numbers is not going to be in the domain. You cannot do that. You have to make sure. To see what is the domain. What is the domain, right? In fact, these 2 numbers, they're both in the domain, right? This number is less. Our domain is from -1, less than -1, or larger than +1, right? So you can obviously see both numbers are in the domain. Both numbers are in the domain, okay? So that's this question. Okay, and of course, we have to check it. We have to check the answer algebraically. Okay, we have to check the answer algebraically. So here we have these steps, right? And we plug in and we simplify, right? We square this piece and we get 1 plus e squared minus 1. So we ended up with log e squared. Log e squared is 2. And for the other solution, we also do in the same way. Okay, so this is how do we solve this question? And I especially like you guys to see the function perspective. Okay, this function perspective, and sometimes it's very helpful. It's very, very helpful. Okay, and I will see all the time, as much as I can, I would like to show you that function perspective. Okay, so let's look at example number 4. Example number 4. In example number 4, I'm gonna show you another perspective, right? So first, domain determination. We got x larger than 2, so we graphed it. And then we do the product rule on both sides, and we got a linear equation, and we got x equals to 5, right? So these steps should not be too difficult, right? You just use product rule and so on and so forth. And we check the answer, and that's the right answer. It's done. It's finished. It's finished by here. Okay, so that's the work you need to do. and that's finished, right? Along with the domain determination. But in this question, I actually do want to give you another perspective. So here, if you look at the left-hand side and you look at the right-hand side, right? I make the left-hand side to be one function and the right-hand side to be another function. And I graph these two functions, f and g, okay? And these two functions are different color. These two functions are of a different color. So what does this if statement say? This if statement basically says, when the output of these two functions are the same, when this output of these two functions are the same. Okay. Okay, so our task here is when it is for what value or input X, okay? It may be plural, okay? Maybe plural, maybe multiple, or inputs X, such that the outputs are the same, okay? So f of X and gx and g of X have the same output. We don't know the output. We actually don't know the output. We don't know the same output yet. So what we did earlier is we have identified the input such that the output. So once we identify the input, so we take that input into one of the functions, f or g, you're going to get the same answer. And that will be the same output. Okay, so graphically, what you see is that that's where the curve, the two curves crosses. The two curves cross each other. Okay, so this is the point. Okay, so this is the point where the two curves cross each other. Okay, this is the place the curve crosses each other. One curve cross the other. Okay, excuse me. All right. So this is another perspective. I hope these perspectives will be very helpful for us to understand. So let's look at example number 5. Example number 5, we have a function, right? We have a log base 2, right? So when we determine the domain, we take the whole of the part that being taken logarithm of, right? The rule of function applied to this whole piece. So this whole piece has to be positive. So when we set it up, okay, we ended up solving this inequality, quadratic inequality, okay? And we found the x-intercepts, and we know there are multiple ways to solve it. So here I'm using the function way to solve it, right? And we want the piece of the function to be positive, not equal to 0. So you can see on the graph, the x-intercept -1, 0, 2, 0 are in circle. They're not included. And you can use interval to express the same thing. Okay? So, and the domain will be x less than -1, which is all of these, or larger than 2. Right, so these illustrations hopefully will help you to understand. Okay, if you have any questions, please let me know. But just out of curiosity, right? How does the graph look like? How does this graph look like? So let's take a look. This is how the graph look like. Right? Log base 2 of x squared minus x minus 2. And you wonder that these, you can see the graph is right here in the domain, and in the middle, right? If you put all two graphs together, right? This is the graph of the parabola. You can see logarithm only can only work on the positive part, the positive piece. With the green piece is the logarithm function. Okay, this is the in green. Okay, and the black piece is the parabola. Okay, the black piece is the parabola. And what is the blue? The blue is y equals to 2, right? Because we want that, we solve the equation of that equals to 2, right? So that's, so if you see this picture, okay, so let me give you a good, so the green, this is the green piece, is that green piece. Okay, we have two pieces. We have two pieces, two green pieces. And this, the parabola, the positive part get to be taken logarithm, get to take logarithm, right? And equals to 2, the blue curve is equals to 2. So the output is equals to 2. Output equals to 2, then that crosses the curve, the green curve at 2 places. And the output is what we're looking for. I'm sorry, the input is what we're looking for. Okay, it looks like it might be -2 or 3. Okay, so we're gonna use algebraic way to solve it. Okay, we're gonna use algebraic way to solve it. And this is the picture which entirely is log base 2x. Okay, so it's just this piece. Sorry. It's just this piece. Okay. So this piece, the green. Okay, that's the green. The domain is right here, right? The domain, you can see the curve only show up on the domain piece. Okay, the green is this function, and the curve only show up on the domain piece. And the less than -1, the x equals to -1, those are the vertical asymptote. Those are the vertical asymptote, okay? So let me mark it. Let me mark the vertical asymptote. Okay, we got vertical asymptote. X equals to -1. So here, so that's the vertical asymptote. And there's another one, which is x equals to 2, right? And that's another vertical asymptote. And there you go. X equals to -1, x equals to 2. These are the two vertical asymptotes. The two vertical asymptotes, right? So then we're pretty clear about the situation, right? We draw the horizontal line. The horizontal line crosses the curve twice, and the solution we're looking for are the x value, are the inputs. So we're looking for the inputs for these two numbers, right? And we know how these points look like. We don't know the input look like. Input equals 2, but we know the output is 2, right? And for this point, same thing. We don't know what's the input, and we know the output is 2, right? You can see these ideas are very similar to what we've done with other functions, right? It may be exponentials, you know, trig functions, and so on and so forth. So the rest is just algebra. The rest is algebra to identify the points precisely. Okay, using definition, right? Omega is this piece, and the triangle is 2. So omega equals to 2 squared. So that's subtracting 2 squared on both sides. We get x squared minus x minus 6. So we get x plus 3, x plus 2 times x minus 3 equals 0. Using principle number 5, we got the solutions. And both values are in the domain. You see -2 is less than -1. X equal to 3 is larger than 2. They are in the domain. Here, I want to remind you guys one important thing is that just because you get a negative number, it does not mean it is not in the domain. You really have to see what the function is. The function, the domain of the function may be, like these two pieces. We have like in these two pieces, right? So both solutions actually are in the domain, right? So you cannot just blindly say, oh, I got a solution that's a negative number, so it must not be in the domain. You have to look at what the domain is. That's why we ask you to determine the domain first. Okay, and if you look at the curve, right? If you look at the curve, ooh, that's a very interesting curve, isn't it? And in fact, this function is actually not one-to-one anymore. Okay, so always make sure you have that function perspective. I think the modern technology make it easier to graph these functions. Okay, so make use of it. You could take advantage of it. All right. All right, so we have two solutions and they're both in domain, and we check them algebraically, and they're both solutions. They're both solutions, right? You plug in -2 on the left-hand side, and you get, this is a 4 minus -2, that's a +2. So this is 6. 6 minus 2 is 4. So we got 2. For x equals 3, you plug in, you have 9 minus 5, so that's 2. So we get 2 again. So in the end, we get 2 solutions. So by this time, actually you're finished. We are done. Okay, we are done. You're done. What I meant here is that if you just do this part, you're finished. Solution is found. Okay, that's okay. That's good enough. That's good enough. Okay, that's what I meant. If you just show this much work, you're finished. However, we try to make that experience more, we try to make this learning experience richer. Okay, so we introduced these graphs, right? These graphs is not difficult to find. And we eventually, when we found these solutions, when we want to see where it is, the solution in the graph. And here it is. For the solution -2, the output is 2. For solution 3, the output is 2. So we got 2 solutions. So this perspective, which is the function perspective, right? Make us see better what we are actually doing, right? We know output, and we're looking for input, and the graph help us to identify how many solutions there are. Okay, so this is the this is one other examples, right? Which one is this? Let's see, number 5. Okay, so we've done number 5. We have more. Okay, we have lots of interesting examples. And I'm not going to do all of them, but I'm going to show some of them. I'm going to do some of them, okay? And this one I'm about to do is actually number 16. Number 16. You know what? I'm actually going to create a new example. We're going to do 16 later. Okay, this is example number 6. I'm just thinking out loud. I want you to see some differences, okay, which is very important. This is example number 6. And of course, we have the same title, solving for a determined domain and solve for something. And this one, I'm solving for, actually, I'm going to be tweaking number 5. I'm going to be tweaking number 5. Okay, because I want to see some very important differences. And this one I'm going to do is that, whoops, plus log base 2 of x minus 2. Okay, the previous example was this, right? The previous example was this. The previous example. Okay. Then you may say, they should have the same solution, aren't they? My answer to that is no. What makes the big difference? Okay. In comparison to example number 5. Example number 5. Right? Then you would say, well, if you do log base 2, right? If you do log base 2, and if you factor, right? If you factor this inside, you're gonna get log base 2 of x plus 1, right? X plus 1 plus log base 2 of x minus 2, right? Wouldn't that be the same? Are they the same? My answer is no. Big difference, big difference. Why? Why? Because when we are doing this, right, you have to make sure both are positive. In this situation, you don't have to guarantee both are positive. If both are negative, they multiply, okay? Say, if you write it this way, is this guy having the same domain as this piece? The answer is no. The answer is no. Because this domain, the domain for this piece, you have to guarantee both are positive. Okay, so let's work it out. Okay, let's work it out. We know the domain for, right? Domain for example 5. For example 5, right? We work it out. We worked it out. This piece, right? So I'm going to copy the whole piece here. We know the domain for example number 5. We had that. Okay. So domain for example 5. So now when we look at example 6, what is the domain? The domain is you have to work it out separately. Okay, so this has to be positive. Okay. And x minus 2 has to be positive. All right. And then you have two statements, right? X is larger than -1 and x is larger than 2. And combining these two conditions, what will happen? Larger than -1, larger than 2. If we combine these two, we only have larger than 2. Okay, larger than -1, right? Larger than -1. So let me give you some details. Larger than -1, right? Larger than 2. And that combination will give you what? That combination will only have x larger than 2. Okay, that combination that we get the domain for example 6 is x is larger than 2. X larger than 2. So you can see big difference. Okay, so let me graph this before I show you any further, right? So for the domain, okay, so that red piece, and there's a circle, right? We have a red circle here. So that's a domain for example 6. Okay. And if you look at the picture, you still remember the picture, right? So if I graph this function, let's see how the picture look like. Oops, I put it in the wrong place. But let's look at the picture. That's the picture. Now, it's not complete yet, okay? I need to make some adjustment. There. It's half of the picture of example 5, right? Why? The fundamental reason is in the domain. The fundamental reason is in the domain. So when we use the property of logarithm property, the product property, right? The product rule, quotient rule, we need to remember, we need to understand, right? The curve, anything you take a logarithm, okay? Right here. This must be positive, this must be positive. The product must be positive. So all three must be positive. Okay. This must be positive, this must be positive. Positive times positive equals to positive. But why we have such differences here? Because the order of operation, okay? In this operation, for this function, right? Okay. So in the case of example number 6, right? We need to guarantee this is a positive before we can do what? Before we can do the product rule. Okay. But in the example number 5, right? We just need to guarantee the order of operation goes like this. Okay, so let me show you the order. The order is saying, okay, X is the input. And this input will first apply this function. Okay, and this output will be applied the logarithm. Logarithm base, whatever. And produces output. And we want that output to be 2. Okay. On the other one, if you look at the flow, what happens is that you have input, right? For input, you're going to do X plus 1, right? And this X plus 1 has to be positive coming out. And then you do logarithm, right? Log base 2, omega, right? Whatever you apply, and it produces an outcome, okay? And we don't know what it is. And for the same input, right? Let me do something like this, okay? I really want to explain this well to you, so be patient with me. And over here, I'm going to have 2 branches. Okay, just like that. So one is X plus 1, and one is X minus 2. okay? So the input will given to x plus 1 and then produces, it will do a logarithm. Okay, so this piece will be doing the logarithm. And this piece will be doing the logarithm, right? So this will be done first. And this will be done, it doesn't matter what the order, right? So x plus 1, but they both must be positive. They both must be positive. So then we do the logarithm for both. And then we're going to add them, right? Adding them, adding the two. Okay, so the outcome, they both have output. And these output, this output 1, and this is output 2. Output 2. And we add these two output, right? So output 1 plus output 2. 2. And the sum is 2. That's what it means. So at this point, x plus 1 has to be positive, and x minus 2 has to be positive. On example number 5, we don't have such requirement. Okay, where's 5? Whoops, where's my 5? There, okay. You have input, and as long as the output is positive, right? We know that this can be positive for x is larger than 2 or x less than -1. So this piece, right? If you factor this piece, you have x plus 1 times x minus 2, right? If both are positive, you get a positive. If both are negative, you also get a positive. That's why we have two pieces, that we have two pieces of curve in example number 5. And for example number 6, you only have one piece. We only have one piece. Okay, so I'm going to put this side by side for comparison. Okay, I'm going to put this side by side for comparison. Okay, this is very important to understand. So these are the pieces, right? So this has only one piece. Okay, so I'm going to put this side by side. Okay, example number 5 and the example number 6 side by side. Compare. Okay, so I'm going to put these things together for your examination. Okay, first thing, this is example number 5. Example number 5. Okay, and the second thing, this is example number 6. Example number 6. The flow, right? The flow of operation for example number 6 is such, right? Output 1, output 2. Okay. For example number 5, that's the flow. That's the flow. Okay, that's the flow. Let me make 125% so you can see the whole thing. Okay, graph domain wise. Okay, domain wise, I'm going to add a couple of rows. Domain wise, right? For example, number 5, the domain started with that piece. Okay, and over here, the next step. And then finally, the domain is that. This is the domain. This is the domain. Okay, that's the domain. For example, number 6, the domain determination is that both must be positive. Where is it? Here. Both must be positive. Okay. Over here. Like that, right? And the domain, of course, finally, it would be x is larger than 2. Okay, so these two are different processes. They're different processes. Okay, so anything going into logarithm, they have to be positive. And here is saying, okay, you just get the product, right? So getting the positive product, you can have 2 positive and 2 negative. That's what sets it apart. That's why the picture-wise, right? So let me show the pictures. Let's show the pictures, right? The domain, for example, for 5, right? The domain for 5 is this. And the domain for 6, right, is larger than 2. Is this. Okay, so let me make it comparable. -5. Oopsie. And this piece, I'm going to make it comparable. Okay, you can see that's make the major difference because the process are different, the flow are different. Okay, so example number 5, example number 6, that's how they're different. That's how they're different. Okay, I hope I have made that very clear to you. Okay, is that whenever you have input for any logarithm, you have to guarantee that input is positive. So this must be positive, this must be positive. Okay, and the graph of these two curves, okay, that's where we see big difference, right? This is the graph for number 6, right? Because your curve, right? Because the curve, right? And what is the graph for number 5? We have that curve, didn't we? So let's bring it back. And that's the green. That's the green piece. Big difference, right? So if we have it equals to 2, if we have it equals to 2, right? So I'm going to graph this same horizontal line. I will also going to have this is 2. The line, we're also going to draw this horizontal line, which is 2. And I'm going to make some comparative adjustment to the graph, right? You can see that big difference is shown because the domain makes such a big difference. Domain makes such big difference. Okay, so I make the picture more better sized, right? So here we go. Okay. So this way, side by side, you can see example number 5 and example number 6 are huge difference, huge difference. Okay, so domain determination makes that big a difference. Make that big a difference. And of course, do we anticipate the solution? Of course, right? We already anticipate the solution, and this solution actually is going to be what? 3, 2, right? So that red dot is right there. So that's a solution. So in this case, you have 2 solutions. In that case, you have 1 solution. All right. So that procedure flow determines that they're going to have different domain and different, different solution. Okay. So let's finish up example number 6. Okay, let's finish up example number 6. Okay, so with all that said and done the comparison, and of course we already finding the solution is not going to be very difficult. We're going to use a product rule. Okay, so we're going to solve it. Right, we're going to solve it. So what do we have is that we're going to have using product rule. So that's log base 2. We have x plus 1 times x minus 2 equals to 2. Okay, and then use definition, we got that equals to 2 squared. And FOIL the left-hand side, we get x squared minus x minus 2 equals to 4. And we ended up with x squared minus x minus 6 equals to 0. Factor, that we get x plus 2 times x minus 3 equals to 0, right? You can see very similar to example number 5. Right, very similar to example number 5. Of course, we already have the definition. I'm sorry, we already have the domain requirement, right? So we have done the domain. So I'm going to bring the domain here. Okay, don't leave that out, because here we're showing work. Domain is determined, so we just go about to do algebraically. So in the end, we get x equals to -2. Or x equals to 3. Okay. And we're going to check our answer, domain check. Domain check, we know that the domain is x larger than 2, so -2 is not in the domain. So -2 is not in the domain, right? And for x equals to 3, we just check for x equals 3, we need to go back to the original equation. Okay, original equation. Okay, so left equals to the original equation. Okay, and putting the 3 in place, right? And what do we get? We get a log base. We got log base 2 of 4 plus log base 2 of 1. And this latter equals to 0. And finally, we get 2. 2 equals to the right-hand side. Equals to the right-hand side. Okay, so 3, x equals to 3 is a solution. And this is the only solution. Is a solution. It's a solution to the equation, this equation. Okay, this equation is different from the equation in example number 5 because of domain differences, right? And we have, of course, anticipated that solution, which is right here. Okay, so now let's take a second look at these 2 examples, right? They are different because of the flow, because the order of operation, okay? They're very different in many ways. Here, I want to make the picture more complete, right? So we're gonna have the domain be marked 2, 0, and red, and that's a circle, right? I'm gonna mark the the line with the domain. Okay, so these comparison I think will be complete. Okay, these and the vertical asymptote, one more. Vertical asymptote, right? The vertical asymptote, I'm going to put it at, oops. There. Whoopsie. I'm going to have a broken line. Broken line. There. You see this comparison, I think is very complete, all right? We have the same, we have the coordinates set up the same way. So, -3, so I want to make it even better. Would that be even better? No, 4. So we make it so comparable. So comparable. There you go. There we go. Okay. Excuse me. Okay. So I hope this is clear to you. Okay, I hope this is clear to you. We have other examples of similar nature, but this example is the additional example that I'd like to put out for you. Other examples, other homework questions, I want to go over this one, number 18. Okay, number 18. Okay, that would be my example number 7. Okay, and it's still the same narrative. Okay, we want you to do the same thing. We want you to do the same thing. Okay, so we got log base 2 absolute value plus 3 equals to 1. Okay, domain, let's look at domain. Let's look at domain. Right, domain wise, the absolute value of x is always at least 0. Okay, this is always a positive or 0, right? So x squared, absolute value of x plus 3, that's going to be larger than 3. Larger than 3 is larger than 0. Therefore, the domain is all real numbers. It's all real numbers from negative infinity to positive infinity. Because it's guaranteed the input is always going to be positive, right? So let's just solve it. Okay, let's solve it, right? So we're going to use definition. Use definition, that means that this is going to be 2 to the power of 1, sorry, right? And then what do we get? We get absolute value of x equals to -1. We subtract 3 on both sides. Does this one have solution? No, there's no solution. What's going on here? What's going on here? Okay, what's going on here? Well, no solution. Every step is checked correctly. If we look at the function perspective, of course, by this time you're done. Okay, by this time you're done. The function perspective, right? So you have the function here. This is our function, and we want the output to be equals to 1. That's an interesting curve, isn't it? Because all real numbers, right? All real numbers. So when you put these curves together, isn't that really interesting? Isn't that really interesting? You know, when I was a student, right, graphing is not always so easy. Graphing is not always so easy. So what happened is that when I was a student, we actually didn't see this perspective. We just do it algebraic way. We just did it algebraic way, okay? So here we got, let's make it 5. So this is the picture. This is the picture, okay? You can see the picture for that one is everywhere. But when we have the output equals to 1, we're gonna draw a horizontal line. We're gonna draw a horizontal line, okay? That horizontal line, I'm gonna make it red. No touch, no touch, no touch, no solution. No touch, no touch, no solution. If you look at the picture, it's very obvious, right? It's very obvious. And the other thing is that you can see this piece is already guaranteed, right? There's another perspective. There's another perspective can justify this no solution situation. Is that knowing log base 2 function is an increasing function, right? This increasing function, that means this is going to be larger than log base 2 of 0 plus 3, okay? Because absolute value of x is always at least 0. So I take the 0 to substitute absolute value of x. Of course, the entire thing is going to be less than the original. And this piece is also going to be larger than log base 2 of 2. And of course, that's larger than 1. So this whole thing is larger than 1 for sure. Of course, it's never going to be equals to 1, right? Because it's always larger than 1. Now it comes to how do you present the solution, right? You can present your solution as I did here. That would be a good presentation. Or if you want to do the function perspective, provided you go through the trouble to graph or sketch, right? And the other thing is that you can use this statement. Okay, you can actually using this one statement to say there's no solution. There's no solution. Okay. So example number 8. Okay. Example number 8, I'm going to make it, I hope maybe this will be the last example. Okay, we'll see. Okay, we'll see how, what else is new and what else will come up. Okay, I'm looking through the homework questions. I think this will be the last one we go through. Okay, I don't want to make this lecture too long. And we're still trying to determine the domain. And the equation we're solving is as follows. So it's ln x squared equals to ln x, right, squared. Okay. Notation wise and the order of operation wise, because we're going to determine the domain, right? Domain and the notation. First, let's talk about the notation. Notation basically is talking about the order of operation. Okay, so I'm going to put a table as a comparison. Okay, so this piece means you have input x. Okay, hold on, x, right? Input x, and then you square that function, right? and then you give it to logarithm. Okay, so that's what you give the input for ln x. Okay, so I'm just going to put it below me. Okay, and then produce an output. You produce an output. So this x, right? You need to guarantee x squared is positive. Okay, you need to guarantee x squared is positive. What will make x squared is positive, right? So let me put a column here. This process requires us to have x squared must be positive. What will guarantee, we remember we solved this equation, solved this inequality. What will guarantee x squared is positive? Well, if we need to guarantee that is positive, right? Then x can be any number. X can be any real number. That x can be any number but 0. Okay. How about the other one? The other one's flow goes like this. We'll have input, and this input will be given to natural logarithm. So we produce ln x, and this output will be squared. This output will be squared. Okay, you can see the difference, right? So this output is going to be any real number, negative infinity to positive infinity. But this output is going to be always at least 0. They have different range because of this process. As a result, because x is given to the ln function at first, so x must be positive, right? So you can see these two functions on both sides, they actually have different domain and even different range, right? Borrow the ideas we had earlier. Okay, borrow the ideas we have from earlier. If we treat this one as a function, right? If we treat this one as a function, and we treat the other one as another function, right? These two functions are actually entirely different. So let's look how they look like. Okay, so I'm going to graph f. Okay, I'm graphing f. This is my f. Okay, this is my f. This is my f. Okay, how about my g? My f is black, right? So this is a black curve. My g, this is my g. G, I'm going to choose a different color. Okay, what color shall we choose? Green. Let's do green. Green. Okay, so the second one is a green. Right? You can see how different these two functions are. Just like we anticipated, the range for this function is all real numbers. It can go as low as possible, as high as possible. The vertical asymptote is the y-axis. Okay, the vertical asymptote is the y-axis. And then we have two pieces. Okay, the black one is ln x squared. The green one is the green here. The minimum, the lowest point is 0. So when we put these two together, what are we trying to do? We're trying to find when, okay, for what value of x, okay? So this statement is telling us we want to have this, well, we want them to have the same output. So when could they have the same output? So this statement is for us to find all possible input, find all possible x, such that the outputs, okay, f of x equals to g of x. Same output. Same output. In other words, where do they cross? Where do they cross, right? This picture already show us where they cross. They actually probably cross at x equals to 1. So the picture actually tell us the solution already. The picture tell us the solution already. All right, so these are the discussions which typically would typically not show, because when you solve these equations, it just goes straight to it, right? But I think the function perspective is a very interesting one. It's a very interesting one. Okay, I enjoy this process of seeing these perspective, and I also like to share this with you. Okay, so this is notation wise and function wise, right? Notation and functions, the different graphs, right? All of these different perspectives. And secondly, from the algebraic properties, right? From algebraic properties, right? We're talking about these, which property would apply here? The power property would apply to the one on the left, but it doesn't apply to the one on the right, okay? So power rule, okay, applies to this piece, which equals to 2 times ln x, okay? And this one, however, this property does not apply to the second one, because the second one means ln x multiply ln x. This one, the first one, means ln x, because we have 2 of them, right? ln x plus ln x. So that's the major difference notation-wise as well. So algebraically, okay, so algebraically different, okay? So notation, graph, we see all of these differences, right? So without further ado, so let's dive into the algebraic work, okay? So this will be the typical, okay? So let's solve, right? Determine and solve these equations. Okay. So of course, we first determine the domain. So when we determine domain, we have to require this piece is larger than 0, right? And that piece and x is larger than 0, right? So these and. Okay. So the final domain, where this one, you get x cannot be equal to 0, right? You get x cannot be 0. And this one, you get x has to be positive, right? So the common part would be what? The common part is x has to be positive, right? Not equal to 0, meaning you have, let me put this there, -5, +5, right? Not equal to 0, meaning you can have all of these, all of that, right? Not equal to 0 means you can have all of these, right, not equal to 0, not equals to 0, right? Larger than 0 means you can only be on this side. And of course, we want that to be and, right? And therefore, the final domain is the solution must be in is x is larger than 0. Okay, so we're going to show that on the graph. Okay, so we're going to have a circle at this circle at 0, 0, right? And we also mark the domain. All right, so that's the domain. Okay. Excuse me. I got a cold. All right, let's solve it. Okay. When we solve it, we have this piece and we have that piece, and we know that we can apply power rule to the left-hand side. So we're gonna have 2 times ln x equals to ln x squared. Okay, so we're gonna let u equals to ln x. Okay, we're gonna do a substitution. So when u is introduced, we have 2 times u equals to u squared, right? And we're gonna solve this equation. We got u squared minus 2u equals to 0. Factor u times u minus 2 equals to 0. Okay, so then we got u equals 0, or u minus 2 equals 0, principle number 5, right? Principle number 5. So in the end, we get, of course, u equals 0 or u equals to 2. U equals to 2. Well, this is not the end, right? Because finding u is not what we want. We're finding x is what we want. So for u equals 0, for u equals 0, what do we get? That means ln x equals 0, right? That means ln x is equal to 0. And solving this equation, of course, x equals to 1, right? X equals to 1. Okay, and for u equals to 2, for u equals to 2, we get ln x. We get ln x equals to 2. Equals to 2. And the consequence will be x equals to e squared. We got 2 solutions, don't we? We got 2 solutions. But we saw the picture, there's only 1 solution, isn't it? Does that mean there's a solution over there, higher up there, right? Isn't that interesting, right? So sometimes when we have the picture, we do the algebra, we have to look back and forth. Maybe our picture isn't complete. Maybe our picture isn't complete. So let's make it complete. Okay, so we're going to have a more complete picture. And this piece is going to be, so here, -4, right? Sure enough, we actually have two solutions. This is a warning sign. So that this tells us, you know, graphing is good, but any picture we get from the equipment, it may not be complete. We have to set it up complete, right? The other perspective is that you have to do algebra graph back and forth. Okay, back and forth and back and forth. Okay, so we get two solutions, right? Isn't that interesting? Isn't that interesting? So the first point, right? The first point, so by this time you're done, right? So solution, we have solutions, right? We have solutions. The solutions are x equals to 1. Or x equals to e squared. Okay, so we get two solutions, right? But what is the perspective that we put it on the picture, right? Because we saw the perspective is here, right? These two are the same, right? The output are the same. So what is that output? Obviously we have two outputs, right? So we need to, let's check the answer, okay? But for x equals to, because they both are in the domain, okay? Don't get any, don't get confused because they both are in the domain. Okay, so for x equals to 1, what is the output? The output is 0, right? So this is 1 and this is 1, so that output is 0. For x equals to e squared, right? And what is the output? The output are here. I will show you guys how to show work. Okay, don't worry about this, right? And we have a summary. So this is going to be e squared. Okay, x is e squared. So this is x is e squared. And this is e squared. And what will be the output? The output is 4, right? Because this is e to the power 4. ln e to the power 4 is 4. So we got these 2 points. So finally, we can put a points on the graph, right? The first point obviously is input output, right? So that one is input output. And the second one is input is e squared. And the output is 4. Okay. So these are the 2 points that we're going to put on the chart, put on the graph. Okay, we got 2 solutions. Isn't that interesting? So this is 1 dot. There's another 1 dot, which is 1, 0. There. Right? So I will summarize. Okay, don't worry. Okay. These 2 are solutions. Well, these are 2 inputs such that the 2 functions have the same output, right? We know the differences between these 2 functions. I think this way of doing these exercises and presenting it to you will be more complete and make the whole theme of function more interesting. Okay, but in terms of showing work, I will definitely give you a version of work to show. And I'm going to show you the work, how to show work. Okay, how to show work. So in terms of showing work, I'm going to show you these following. Okay, in terms of showing work. Show work. Okay, show work. In terms of showing work, right? We solve this, right? Typically it will be say solve for x, right? We have that. You determine the domain and you don't have to introduce u, but if you introduce u, just make it a little clearer. And I'll give you a version that you don't have to show, right? These pieces, you don't need to, okay, typically. But you do need to check. You do need to check. Okay, so we have x equals to 1 and x equals to e squared, right? So for left, so you're going to check the left-hand side and right-hand side. Left-hand side, okay, so this is the left-hand side and this is the right-hand side. Okay, for each number, for x equals to 1, for x equals e squared, for x equals to e squared, you're going to check the left and right. So I'm just setting this up. Okay, so x equals to 1. So here that equals to 0 and that equals to 0, right? Left equals to right. Okay, then you can say this x equals to 1 is the solution to the equation. To what equation? Well, I'm going to copy that equation right here. Okay, that's how you check your work. Then you can see actually both values are in the domain. Okay, domain check. Okay, left equals to right. So this piece is checking x equals 1. Indeed, it's a solution. For e squared, you will plug in the left. And that equals to 4. You plug in the right. And that equals to 4 as well. And you tell the reader left equals to right. Okay, then you say, is it necessary to tell left, to point it out, left equals to right? And my answer is yes. Okay, to make you a point, sometimes you just have to point out the most obvious, so the reader have no doubt. You're just leading the reader to your objective, to your purpose. Okay, which is convincing the reader that you got everything right. You are convincing. So in terms of showing work, and this is how much work you can show. You can see this question actually it's no small business, right? There's so much involved. If you expand and look at the function perspective, it's rather interesting. It's rather interesting. And it gave us a lot of insight, right? So algebra graph, we compare back and forth and we see, oh, we don't want to miss anything, do we? No, we don't want to miss anything. So this is the lesson for today. This is a lesson for today. Let me see if I can show you the whole piece. The whole piece. Yeah, it's hard to show the whole piece, right? The whole piece. So you determine the domain. Graphing the domain is not necessary. Okay, I put it here, right? You don't have to. This is sufficient. Then you solve it. Okay, is it possible not to solve it using these? Sure, you can solve it without introducing u, okay? No problem. And if you like that way, go for it. But you must check your answer. You must do the domain check and you do the other check. Okay, you check left equals to right, right? The format that I check the solution is pretty standard. It's pretty standard. So follow this if you, I hope you follow these routines, okay? It just make it more logical, All right, so without further ado, I think that's all for this lesson.
Thank you for watching. Until next time. Bye.